Hi guys, in this class I would like to derive expression for energy stored in a capacitor with air as medium. So this is the expression for energy stored. So in the previous class we derived capacitance of a capacitor. Suppose what is a capacitor? Capacitor is a setup. So two oppositely charged plates which is having positive charge and which is having negative charge. So they are separated by a certain distance. So here the d is the distance between them. Now here they acquired the charge due to because of by applying the potential difference. Now if I can write the capacitance of a capacitor, this capacitance C is equal to Q upon V, charge per potential. So this is the expression for capacitance of a capacitor. But here we need to derive the energy stored. So this capacitor stores energy. So to that we need to derive an expression. So for that, let me take uncharged plates. So let me take two uncharged plates. So this is the plate 1, this is the plate 2. So let me label as 1 and 2. So initially these two are the uncharged. Now imagine like this, I am doing charge, it means I am carrying a positive charge. So from plate 2 to plate 1. So this is doing by me. So I am carrying a positive charge from plate 2, plate second to plate 1. So in that case, the plate first will acquire positive charge and plate second will acquire negative charge, because from here if you can take it out positive charge and that will becomes negative. Now at this moment let me take this as having negative potential, so which I can show as minus q dash, and which is having positive potential plus q dash. Okay, now here I do not apply any external source. Here work done by me. I am doing work to bring charge from second plate to the first plate. I did work. Now at this instant, at these situations, at this situation, if I write the expression for potential, so potential expression, what can I write? Potential capacitance C is equal to Q upon by V. Since it is having Q dash, I can write the potential expression for potential. I can write that V dash, potential expression V dash equal to Q dash upon C, if C is the capacitance. If C is the capacitance, therefore V dash equal to Q dash upon C is the expression for potential. Now suppose at here, if I am doing work to carry a small positive charge, in this situation I am carrying a small positive charge dq dash. I am carrying a dq dash from second plate to first plate. So if I am carrying small positive charge, what is the work done by me? So I am doing work a small work. So the work done, so small work I can label as dw, which equal to, so we can write that work and the potential relation, so that equal to v dash times dq dash. If you remember the potential formula, potential v is equal to work done per charge, work done per charge. So from that work done we can write potential times charge. So the work done, the small work done by me, since I am only carrying the charge, positive charge at the time, so dw equal to v dash times dq dash. So let me take a second equation. Now in the second equation, if we can substitute the above equation, if we can label this as second equation, this is my second expression. Now if we can substitute 1 in 2, therefore dw equal to, so q dash by c times dq dash. So that is the small amount of the work I did to bring a positive charge from second plate to first place. So to calculate the total work, to bring total charge of capital Q from second plate to first plate. So initially the first plate is having no charge because I have taken the both are the uncharged plate. So initially they both are uncharged. So my aim is that to bring a positive charge from here to here, to make it as positive charge, and it obviously makes as a negative charge. So the total work done by me in this case, so I can calculate the total work done as W equal to, I need to do the integral dW, which equal to, for the limit integral 0 to capital Q, because 0 is the initially the charge is, the plates are uncharged, so they are uncharged, so that's why my lower limit goes to 0. Now I have to make it them as a total charge Q, that's we take as a positive Q. Integral dw 0 to Q, I need to do integration upon Q dash by C times dQ dash. Now if we can do the integration and substitute the limits, now work done equal to Q dash dQ, it's just like integral x dx, its formula goes to x square by 2, so I can get it here Q dash square upon 2c times 0 to capital Q. Now in the place of the Q dash we can substitute the limits, so I can get Q square by 2c minus 0 is the work done. Now finally I can add the work done expression, work done equal to half Q square by c. Now this is the work done expression, so that is the amount of the work I did. So but work is a form of energy, so whatever work I did, so that work will be stored in the form of potential energy. So this work done is stored as electrical potential energy. This work done will store as electrical potential energy. So I can write that electrical potential energy as capital U. So we can take that as symbol as capital U. Therefore electrical potential energy capital U equal to half Q square by C. Now it is having different forms, since we can write that in terms of, suppose since Q equal to CV, so if you can substitute in the above expression U equal to half C square V square by C, so you can cut one C, in terms of that you can get half CV square. So this is also expression for potential energy in terms of capacitance and potential, and this is the expression for electrical potential in terms of charge and capacitance, half CV square. Now if you can write that further simplification in terms of the charge and potential, since I can write it here, since capacitance C is equal to charge upon potential, therefore you can write potential U equal to half, in the place of C if you can substitute this value, Q by V times V square. So one V gets cancelled, we will get half QV. So this is the third expression for electrical potential energy in terms of charge and potential. So finally I can write that electrical potential energy. So electrical potential energy. So in terms of charge and capacitance, U equal to half Q square upon C, or U equal to half CV square in terms of charge and potential, or you can take potential U equal to half QV. So these three are the three different expression for electrical potential energy. All are the same. So whatever the work I did to transfer positive charge from plate 2 to plate 1, so that work is stored in the form of electrical potential energy in the capacitor. So this is the expression for electrical potential energy if the medium is air. So here the case is given that the medium here I have taken as an air as a medium. This is an air as a medium. Suppose what happens if we take any dielectric medium. So instead of air, if you can take dielectric medium, so if you can write that as a special case, that special case if you can take when air is replaced with a dielectric medium. When air is replaced with a dielectric medium of dielectric constant kappa, of dielectric constant kappa. So if instead of air, if we are having dielectric medium, so where the change takes place, change is only the capacitance. Capacitance of a dielectric medium will becomes K times capacitance of a capacitor with dielectric, K times the capacitance of a capacitor without dielectric, and the potential V becomes V naught. So here C is the capacitance of a capacitor with dielectric, and C naught is the capacitance of a capacitor without dielectric, and potential gets changes, and we can find a change in this expression of Cv square. So this expression will be changes as, we can rewrite that energy stored, as the energy stored becomes energy stored becomes U equal to half Cv square is the expression we derived. So in the place of C, we can substitute this value. C is equal to capacitance of a capacitor with dielectric, kV naught, and in the place of V, we can replace the potential V naught. Therefore, expression U equal to electrical potential energy half K times C naught, and here becomes V naught square. So here K is the kappa. So U equal to, I can write kappa front. So it is kappa times half C naught V naught square. If you can consider, if half C naught V naught square equal to U naught, potential energy, initial potential energy, therefore potential energy with dielectric. So this is everything with dielectric. U equal to kappa times U naught. It means if the dielectric medium is present, the potential energy is also increases. How much time it increases? It increases, energy stored increases kappa times. So that the dielectric constant, which is having the material which is having more dielectric constant, that material if we can place inside the capacitor, the potential energy storage is also increases. So if we can write that capacitance is also increases with kappa, and potential energy is also increases with kappa. So that is the importance of the dielectric medium. Now let's see how this potential energy changes. Energy stored changes in series combination of capacitors. So energy stored in series combination. So if we can see in series combination, so this is a very important statement you need to remember. In series combination, charge is constant, Q is constant. So in series combination, Q is constant. So by taking this statement, so how we can replace that? Since suppose total energy, I am having different capacitance of capacitors C1, C2 and C3 and so on. So I connected in series. If you connect in series, the total energy, so capital U, if you can write that in terms of half Q square by C. So in the place of 1 by C, I can write half Q square upon 1 over C. So 1 over C is nothing but the capacitance in series. 1 over C, you can write that 1 over C1 plus 1 over C2 plus and so on 1 over Cn, if they are connected in series. Now if I split that expression, the total energy U equal to half Q square upon C1 plus half q square upon c2 plus half q square upon c3 and so on. So this is also you can write the total energy U equal to sum of the individual energies. If you can write this as U1 plus U2 plus U3 and so on. So the total energy in series combination, if you can combine capacitors in series combination, the energy is also will be added. There is no decreasing of the energy, just energy will be added of the individuals. Similarly, if we combine in parallel combination, suppose if you are having different capacitors, the capacitance of capacitors C1, C2, C3 and so on, and they are connected in parallel. So in parallel combination, what is key point in parallel combination? The potential V is constant. So in series combination, how the charge is constant? So in parallel combination, the potential V is constant. Not only that, if you remember parallel combination, total capacitance C equal to C1 plus C2 plus C3 and so on. So if I write the expression for total energy, therefore the expression for total energy, now since potential is constant, now I can take the expression for energy stored half CV square, since potential is constant. Now in the place of C, if we can replace the total capacitance C1 plus C2 plus C3 and so on. Now if you can split this expression, half C1 V square plus half C2 V square plus half C3 V square and so on. Now this is also equal to the capacitance of individual capacitance U1 plus U2 plus U3 and so on. Therefore the total energy is algebraic summation, is sum of the individual energies in the both in the series combinations also, in the parallel combinations also. So this is the key point. So when we connected capacitors in series or in parallel, if you can take same capacitors, suppose same capacitors, same capacitor of capacitance C equal to C1 equal to C2 equal to C3 equal to C4 equal to 1 microfarad. When we connected these in series and in parallel, so the capacitance in series is not equal to capacitance in parallel. Yeah, that's correct, because in series the combination will be gets as an 1 over, but in parallel the combination becomes, in series it becomes 1 over 4 microfarads, but in parallel it becomes as an 4 microfarad. But the energy stored in the both of the combinations, but the energy stored in both the combination is same. So this is the final statement. So this is all about energy stored of a capacitors when the capacitors are connected in series or capacitors are connected in parallel, and the expression for energy in terms of capacitance and potential. So these expressions, the three important expressions, you can learn carefully. The relation between of the capacitor capacitance of a capacitor with the charge and potential energy U equal to half Q square upon C, and the potential energy versus capacitance versus potential, capacitance U equal to half CV square, and the potential energy, charge and potential of QV. So I can encourage you to remember this expression of CV square. So from this we can bring it out the above two expressions. Since we know the capacitance and charge relation C equal to Q by V, we can bring it out easily.